Hi everyone, myself Mahesh Sherur. So today I am going to explain you the design of research concrete structure subject related to the shear and torsional resistance of pre-stressed concrete member of model 4. Okay. When external loading is applied, the bending moment increases and the pre-stressed concrete beam reaches the stage of decompression in the tension zone. Later, when the tensile stress crosses the flexure cracking capacity of the material, concrete cracks starts developing in the tension zone. Similarly, if the principal tensile stress of the cross section of the tensile stress capacities of the material in the beam cracks start developing normal to the direction of the such principal tensile stresses. So in this figure you may be observing a beam when subjected to a loading. It may be uniform load or it may be a point load. So different cracks you will be observing. This bottom portion of the beam is subjected to a tension force and the stresses, and the top of the beam above the neutral axis is subjected to a compression forces, and at the end there will be a web shear cracks developed due to the stresses and the load on the beam. In this figure here we have made the different sections like A, B, C, D, C1, C2. So in this A portion from here to here there are no cracks, so it is called as no cracking zone, and from end of the A to the B end it is called as web shear cracks. So it will be at the top of the member web shear cracks on the both sides of the beam or a member. And C is the flexure shear cracks. So here it will be developed flexure shear cracks, which is bigger than any other cracks will be developed. This and D at the midsection. Okay, here the flexure cracks will be developed first. Due to this flexure cracks, and C, B, and A will be developed. And C1 is the zone with a parallel cracks. See, this is the zone. Parallel means here this side both sides are equal, so that is called a zone of parallel cracks. And C2 is the zone with a converging cracks. So it will be cracks will be converged. So this is the behavior of the torsional resistance in the pre-stressed concrete beam when subject to a loading. So next one, after cracking the beam is shear resisted by, okay, so if the crack occurs then the shear will be forces will be developed or shear cracks will be developed, then how it will be prevented. So first one, it will be prevented by the vertical component of the inclined compressive force in the concrete in the compression zone. So first one, vertical component will be there and inclined component will be there, that is compressive forces in the concrete in the compression zone. Then second one, double action of the reinforcement bars and the coarse aggregate in the tension zone or the chord. So double action of the reinforcement, so that is nothing but the bending of the reinforcement. Double bar is due to the presence of double bars and due to the presence of shear bars, reinforcement bars, and the coarse aggregate in the tension zone. Then third one, aggregate interlocking along the shear cracks. Then how the aggregates are interlinked in that shear cracks on that beam or the member, that also depends on that. Then bending resistance of the concrete, okay, teeth, that is between two cracks, that is bending resistance of the concrete teeth or the compressive action of the portion of the concrete, that is frame action. So that is bending action resistance also plays important role. Then shear resistance of the uncracked tendon in case of prestressed concrete with a trapped tendon, or called as cracked section with all the reactive forces. These are the five parameters which control the shear cracking in the beam. Okay. The next one, shear and principal stresses. The shear distribution in an uncracked structural concrete member for which the deformation is assumed to be linear is a function of the shear force and the properties of the cross section of the member. So, therefore, shear stress at a point is expressed as tau v is equal to V into S divided by IB, where tau v is the shearing stress due to the transverse load and V is the shearing force. S is the static moment. It is also called as first moment of area. Then I is the second moment of area about the centroid, that is I is equal to PD cube by 12. Then B is the breadth of the section at a given point. Okay. The maximum and minimum principal stresses developed are given by F max, that is equal to Fx plus Fy divided by 2 plus half into root of Fx minus Fy the whole square plus 4 into tau v square. Similarly, F minimum is equal to Fx plus Fy divided by 2 minus half into root of Fx minus Fy the whole square plus 4 into tau v square, where Fx, Fy are the direct stresses and tau v is the shear stress acting at that point. Okay. So next one is the formula. Okay. Shear force at the support. Then in the problems, if you want to find the shear force at the support, that will given by V equal to W into L upon 2. Then maximum shear stress at support tau V is equal to 3 by 2 V divided by B into H. Slope of the cable at support theta is equal to 4E upon L. Then vertical component of prestressed theta is equal to P into slope of the cable. Then first moment of inertia I is equal to or S is equal to A into Y bar. So these are the important formulas which will help you in finding the solutions for the problems. Okay, thank you.